Okay, I'm now recording this session so that those who are not here, they can follow. Okay? Okay, so today we are going to continue these exercises. Did I give you something as homework? I guess, huh? What did I give you? 13 and 14? Hello.
Yes, you gave exercise 8 on page 36.
8? Exercise 8?
Yeah.
No.
We didn't have this in the slide.
Why not?
Because I think your Wi-Fi wasn't working, so you told us you would send us a video.
I did. No?
Really? Because I think we never received it.
You never received the video?
No.
Aha. That's it's a pity. Let me see. That's this morning's class, 200 by week 14 course of Thursday. I put it online. You didn't I didn't send you the link. Maybe I didn't send you the link.
We didn't send the link, and we don't know why you didn't send it.
But you can look on my YouTube account. Everything is there. Huh?
We didn't find it.
Okay, so we have to redo it. So, but if we have to redo it, I need to reprint the course because I need to reprint a few pages because I don't have these pages as a I wrote on the pages already. So give me 1 second and I will print that. Oh God. Okay. Oh God, my Acrobat is not working for some stupid reason, so I have to use something else. Alors, so that was from exercise 8. Where was that? You see my screen now?
Yes.
Okay.
Yes.
So today what we are, so this we did, okay, we did the principal rays, which are the one which is parallel to the optical axis, and it goes through the focal point, and then the one which goes straight to the center of the lens, and the one who arrives from the focal point is going to be diverted parallel to the optical axis. Okay, this was for a convergent lens, and for a divergent lens the situation is a bit different. The ray which arrives parallel to the optical axis leaves in the direction defined by the focal point. The ray that goes straight through the center continues straight. This is still the same thing. Okay. So now we have to take exercise 8. So I'm going to have to print from this page, which is page 36. Print page 36. So let's say 36 to 42. So give me 1 second for this print to come out and we will start. Allez, move it. Okay, it's coming out. It's a pity there was a misunderstanding about this video, because I'm losing one Thursday. No. No. You are the Tuesday class. So it's fine actually. And so the classes, you will be at the end of this course, you will be at the same level as my other class, which is perfect actually. It's perfect. You did it on purpose.
So good, that's fine.
Huh? Yeah. No, it's perfect. Okay, good. Okay, exercise 8. Let me reopen my software. Now you see?
Yeah.
Okay. I have a new webcam which is a bit less complicated psychologically than my iPhone webcam. The definition is a bit lower and the rate of images per second is lower, so that's why you would see it move a bit less, but it's okay. Okay, what do you see in this exercise? Did you try to do it, 8 and 9?
Yeah.
Okay.
8.
8. Okay, 8. Well, the arrows here, they are not marked very well, but you see that this is all the same actually, convergent lens. Okay, this is the first thing you have to look at when you get an exercise. Is it a convergent or a divergent lens? And now we have this object which is here, and we are going to move the object further closer to the lens, okay, until the situation where the object is at the focal point down here. And so we are going to construct the images. So of course there is one of these principal rays which is always the same. Okay, it's the one which arrives parallel to the optical axis. Okay, this ray here is always going to leave through the focal point. Okay, and maybe you have noticed that this ray is exactly the same in all the situations, because it doesn't matter how far the object is from the lens, we always have this light ray coming in parallel to the optical axis, and it always leaves in the same direction. Okay, so I would say, if we want to rationalize work, we could start by drawing all these rays which are the same on all the figures. Okay? And finally, this one is also parallel here and goes away through the focal point. Okay? These rays are all the same. Now, which ray is going to determine the intersection? Well, the easiest thing to do, of course, is to take the one which passes through the center of the lens. Okay? And so here, well, the drawings are a bit small, but basically the intersection is here approximately, and we have an image which is very small and which is inverted. Okay, this image, we say it's inverted because it's below the optical axis. Okay, it's if this is up, this one is down. And is it real or virtual in your opinion? Is it real or vertical, this image? What would you say?
I don't know.
You don't know. So what was the rule? A real image, virtual image. Okay? What defines a real image? You remember?
No.
No. A real image can be projected on a screen. Okay? If it can be projected on a screen, it means that this image is formed by light. It means the image receives light from the system. So we need to have light rays which arrive at the image, and if we put a screen here, we should see something on the screen. Do you think this is the case? Will we see something on the screen here?
Yes.
Yeah, we have light rays arriving, so this image is real. Okay? And in which situations do we get a real image? I recall you that it's with the convergent lens, okay, when the object not between F and the lens. This is written in the course, maybe you cannot read so well here. So when you have a convergent lens and you have an object which is not between the focal point and the lens, then you get a real image. Here you are not between the focal point and the lens, the object is here, so you will have a real image. You want me to show you again with the simulator? You would like that?
Yes, please.
Okay, so let's go. PHET. Where is that? It's this one. Allez, move it. Okay. So here we have, let's put ourselves in the same situation as in the exercise. We have an object, and this object is pretty far from the focal point and further even from the lens. Okay? And what do you see? You see that indeed you have an image which is inverted, and there is light arriving through these rays. Not only these, of course, there are rays everywhere. Okay, maybe I should say that these rays, we just trace them because they have special properties. But of course, there are rays which come this way and which are deflected this way. There are rays which come this way and which are deflected this way. Okay, so the light which is coming out from this point, well, it doesn't produce light, but it reflects light. The light gets reflected in all directions, and the rays which get reflected towards the lens, they get focalized by the lens, and they end up here, and they form an image on the screen. Okay? Now, the exercise, as we said, consists in moving the object closer to the focal point. And what happens if we move the object closer to the focal point? Well, you see that the image is getting bigger and further away. Okay? And then something a bit special happens when we are at the focal point, because here all the light rays are parallel when they get out from the lens. Right? How would you interpret this? What would you say about the image in this situation? Where is the image?
There is no image after the lens.
Well,
the
actually, if you look at that image, you see that it's getting bigger, bigger, bigger. And these lines, they are becoming parallel. So actually, we say in this situation that we have a real image at infinity, because parallel lines, they intersect only at infinity. Okay, so So this is the situation in which you have an image, but this image is projected at infinity. If you want it sharp on the screen, you need to put the screen very far, let's say at infinity from the lens. Okay, but now this is not in the exercise, but I will show you what happens if I push the object between the focal point and the lens. What happens here, you see that these lines here, they are diverging. So you cannot have an image down here because these lines are not going to meet. And so what you need to do here, I will click on virtual image, and this is now going to display the virtual image. You see, if you are between the lens and the focal point with your object, you will have a virtual image on the same side of the lens. Okay? So this corresponds to what I told you. You can have a virtual image if your object is between the focal point and the lens for a converging lens, and you will have a virtual image if your object is if your lens is divergent. Okay? Ça marche? Try to remember this behavior, and you can come back to that if you want, whenever you want. Okay? So in this exercise, we observe only this phase here, okay, from there to the focal point. Okay, so we do all our drawings. Let's go back here. Okay, the first drawing found a small image here. The second drawing, well, this line we already drew it. Now I can draw the line which goes through the center of the lens, and it arrives here. So I have, it's difficult to see, plus it's not very precise because the drawings are small, but you have again an image which is inverted, which is real, and it gets a bit bigger. It's difficult to see. We're going to see it better with the next image. You see that now the intersection is here. Okay, so we have an image which is here, which is getting bigger, which is inverted, which is real. Okay, this is always inverted, real. All these images are inverted and real. Okay. Now for the next one, well, now you understood what happens. For the next one, we have an image which is a bit bigger, a bit further. And if we are now we are not at the focal point yet, so now we trace this, and our image is here. Okay, so we observe the same behavior we saw in the simulator. And when we are at the focal point, I forgot to draw the line which is parallel. So I'm drawing it now. Okay, and now what happens? It happens that if you draw your two light rays, they are parallel, okay, and parallel rays only meet at infinity. So here we say that we have an inverted real image at infinity. Okay?
Yes, but so what does it mean for an image to be real? What's the...
Well, I wrote it here. Maybe, okay, let me write it better. Let me do that clearly. Okay, we have real images and we have virtual images. Okay, let me change pen. Okay, real images are receiving light. Okay, this means that if you want an image to receive light, it means you need somewhere to have light rays which arrive to form the image. So typically the situation is this. We have the focal point and we have some object here, okay, and this object will have a real image here. Okay, I can even draw, if you want, the three remarkable rays. Okay, I can also draw the one which passes through the focal point and then continues parallel to the optical axis. You see now, these three rays, they are bringing light to this point. This point is receiving light from all the rays. I drew only three, but of course there is one here, there is one here, there is one here. There's an infinity of light rays, okay? And all these light rays, they carry light, and this we see because we have a solid line and we have a direction of the propagation of light. So this is a real image, okay? And now if I put a screen here, on my screen I will see the image. There will be light arriving on the screen and I will be able to see an image, okay? And when do you have these images? You have them with convergent lenses if the object is not between the focal point and the lens. Okay, here our object is not between the focal point and the lens. What happens if the object is between the focal point and the lens? Okay, well, maybe I should not do it here. I will do, because this will give a virtual image, so I will do the drawing on the other side. Okay, now what is a virtual image? Okay, it's an image seen by our brain, but which does not receive light, and this means also which cannot be projected on a screen. I will try to explain you this. Okay, for the moment just maybe write it down or just listen to me, it's in the course anyhow. So how can you get a virtual image? You can get it with a divergent lens in all cases, or with a convergent lens, and the object is between the focal point and the lens itself. Okay, can you read?
Yes.
I will give you these, I will draw these two examples. Okay, let's start with the example of the divergent lens. So here I have a divergent lens. Here, let's say this is the focal point. Okay, and let's say I have an object here. Okay, where is the image of that object? Do I have an image? Well, let's trace the rays. Okay, this is the ray which comes in parallel to the optical axis. Where is it going, this ray? How do you compute that?
Through the focal point?
Yeah, the focal point gives you the direction, okay? So you draw a line here, but this is a construction line. There is no light traveling here, and your light continues like that. So the light arrives here, crosses the lens, and leaves. Okay? And now we have...
This is with the divergent lens?
This is a divergent lens. You see it from the symbols here. And the other light ray is going to go this way. So this light ray is bringing some light, but this one is not bringing light. And so we have an image here which is virtual. And why do we see this image? It's our brain which sees this image, but actually our brain gets tricked. Okay? If we are looking at this object, if we are looking, we are behind the lens, okay? We see a light ray which arrives from that direction, so our eye and our brain believes that there is an object on a straight line in the same direction as this light ray. So our brain believes that there is an image here, and indeed we see an image there. But we cannot project it. If we put a screen here, there is nothing. I will give you another example in a moment. Well, I can give it to you now. Let's imagine you have a mirror here. This is the easiest example of a virtual image. Okay? This will be the third example, that's why I put it down here. Leave some space here for the second example. Let's imagine we have a mirror, and here we have some object. Okay? And we are looking at that from here. What do we see? Well, there will be a reflection, okay? So the light which arrives from the object is going to get reflected by the mirror, and it's going to come hit our eye, right? Say yes, so I feel more secure and I can continue. Okay, but our eyes sees a light ray arriving from there, so our eye naturally interprets that as the object is here. Okay, our eye is imagining that there is an image behind the mirror. You can do the experiment with a mirror. If you want to go take a mirror, go take it and try, or try later. Okay, when you look at a mirror, you see images behind the mirror, but of course there is nothing behind the mirror. And if you go put a screen behind the mirror, you will not see anything because the light doesn't cross the mirror. Yet you see the images behind the mirror. These are all virtual images. Okay, you cannot project them. Okay. So this is the situation in which the image is always virtual with the divergent lens, and with the convergent lens there is one situation in which you get virtual images. It is the situation when the object is between the focal point and the lens. Because if the object is here, let's say we have an object here, okay, and let's try to construct the image. Well, okay, let's do it. So we take the ray which is here, and this ray is deflected towards the focal point as usual. Okay, and the other ray which passes through the center of the lens, if you want to draw it, it's like that. So here the rays which are coming from this point, they are diverging. Here we will not have an image, because if we want to have a real image, this point has to form on the other side of the lens by an intersection of all the light rays. We don't have that. But now what do we have? If we extend these lines, and these lines should be not plain lines, okay, because there is no light arriving here, then we will see an image here, and this image here is a virtual image, okay, because no light arrives. But if our eye is here, okay, if we are here looking at the lens, we will see these divergent rays arriving to our eye, and so our eye and our brain will be tricked into thinking that the object is here, where the light rays seem to come from. You understand?
Yes.
Okay?
Yes.
Yes.
So the general definition is a real image is made of light and can be projected on a screen. A virtual image is not made out of light and is something that is created by our brain. Okay, this is the general definition. And in terms of lenses, when you have an object which is outside the focal distance for a convergent lens, you have a real image. If you have an object which is between the focal point and the lens for a convergent lens, or anywhere for a divergent lens, you will have a virtual image. Okay? Ça marche?
Yes.
Okay. Good. You can, for instance, you can do a stupid experiment. You can look at yourself in a spoon. Okay? You realize when you look at yourself in a spoon that you see yourself much smaller behind the spoon. Did you try that?
Yes.
Yeah. Well, it's a virtual image. It's behind the spoon. You cannot project it. You cannot do nothing with it, but your eye thinks that there is something there. Okay? And then there are ways to transform a virtual image with a real into a real image with the lens, but I don't want to go into that. Okay? Okay, did you do the exercise 9?
No.
No.
No. Okay. So let's do it, and maybe before I do 9, let me recall you what we did previously in exercise. Was it 4? Yes. Okay. If you look at exercise 4, it's kind of similar because we have a convergent lens, okay? But here we had light rays which were coming in all parallel to each other, and so they were ending up here all meeting at the same point. Now, and so you remember the construction we did for that? When we have a light ray which arrives which is not parallel to the principal axis, we take a parallel to that ray through the center. This gives us an intersection with the focal plane, and this is the direction in which the ray leaves. You remember that construction?
Yes.
Okay. So here all the rays were arriving in the same direction, so we needed to do this construction only once. In this exercise it's different because all the light rays arrive in different directions, and so we need to compute to do this procedure separately for each light ray. However, there are 2 light rays which we know. We know how they behave. Notice also that this is a divergent lens, so be careful. We did this construction, wait, oh yes. You see, we did this construction in exercise 7 for a convergent lens, okay? And now exercise 9 is just the same for a divergent lens, okay? Okay, well, let me stop talking and let me do it. Here, when you look at that, try to simplify your life. How can you, sorry, I'm just turning this. How can you simplify your life here? Well, for some of these rays, it's easy because you know them. For instance, this one, which is parallel to the principal axis, is going to do what after the lens?
towards the focal point.
Yeah, but be careful, this is a divergent lens, so the light ray has to diverge, and so its direction is going to be given by the line which comes from the focal point. Okay? This one we know for sure. Okay? Then there is another one we know for sure. Which one is it?
The one who passes through well, the line, the middle of the lens.
Yeah, through the center of the lens. And this one goes how? It goes straight. Okay, it's not deviated. So this one you can draw it. Okay, I will leave these two in red and I will do the others in green, so maybe it will help you not to confuse them. Okay, good. Now what about the other ones? Let's start from this one. What should we do for this one to construct the ray which is coming out? Remember, it's a convergent lens, so we have to construct the focal plane here. We construct our focal plane. I recall you that I draw a line, but actually in real life this is a plane, this is a two-dimensional surface. Sorry, voila. Yeah, can you focus please? I hate these automatic things which don't work. Okay, so now we construct the focal plane, and what else do? We draw a parallel to the incoming light ray. Okay, so if I want to draw a parallel to that, I need to do this. Okay, this defines a point which is the secondary focal plane, and so this point is now giving us the direction of the light ray which leaves there. Okay? Are you following me, or you want me to do this construction for one ray to show you?
I don't understand how did you find the point, the green point?
This one.
Yeah.
The procedure, okay, we saw that 2 weeks ago, but maybe you forgot. Okay, let me redo the procedure on a different page with just one ray, because now you're seeing all these rays and it's difficult it's complicated not to mix things up. So let's take one principal axis. Here I will take a convergent lens, so revise these notions. And here I will take a divergent lens. Okay, and let's take a focal distance of 2 centimeters for both the lenses. Okay, this I call F, this I call F prime, and for the divergent lens is the opposite, F prime and F. Good. Okay. If I have a light ray which arrives like this in a convergent lens, the procedure to decide how this light ray is going to leave is the following. You take the focal point, the image focal point, you draw the focal plane, this is the focal plane, okay? Then you draw a parallel to that incoming light ray through the center of the lens. You draw a parallel, and this answers your question. This is how I determine this point. I don't remember who asked me the question. Okay, and so this light ray is going to continue passing through this point, which we'll call the secondary focal point. Okay? So the secondary focal point, you find it as the intersection of a parallel to the light ray passing through the center and the focal plane, right? And we are very happy because this is a convergent lens, and indeed it makes this light ray converge. It forces it to go back towards the optical axis. Now in this case it's different. Okay, in this case let's take approximately the same light ray, and I will do something. Yeah, it's approximately parallel. It arrives like this. Okay, of course it's a divergent lens, so we expect that this ray becomes more divergent after the lens. We expect it to go somewhere like this, certainly not like this, okay, because the lens is divergent. Somewhere like this. How do we do that? We do it by tracing the focal plane, but on the other side of the lens. You see, for a convergent lens we were doing that on the right side of the lens if the light ray arrives from the left. But here the light ray arrives from the left, and we do this construction on the left, and then on top of that we draw a parallel to this incoming ray. We draw a parallel here, and this determines one point here, and this point gives us the direction in which the incoming ray leaves. Okay?
Yes.
It's a bit strange in the beginning, but actually it's fine. So what I am doing now in exercise now is I'm doing this construction for every light ray which arrives, because they all have different directions. So I have to do this for all the light rays which are incoming. Okay? And since I wanted to save some work, I took the rays which are easy to do. Okay? This one is parallel to the optical axis. Okay? So when I draw a parallel to it through the center of the lens, it will take me just here. So this ray leaves following the direction given by the image focal point. Okay? And this one, if I draw a parallel to it through the center, well, the parallel is going to be just the same line. Okay? So it tells us that the intersection between the focal plane is going to be here, and this tells us that this ray is going to go straight. Okay?
Yeah.
Okay. And then I continued with the other ones, the ones we don't know anything about. This one, for instance. For this one, I drew a parallel to it through the center of the lens. This determines this point. And from this point, I have the direction in which my light ray is leaving. Okay? You understand?
Yeah. Yeah.
Wait. Maybe it's better like this if it's a bit bigger. Okay, yeah, it's better. Okay, now let's take the next one, this one here. So it arrives in a direction which is it arrives in the direction of the focal point. So where do you think it's going to go? It arrives in the direction of the focal point, so where could that be going? Well, it's going, yeah, it's going to end up being parallel. My poor eyes, I don't see anymore. Voila. This one is going to go parallel to the optical axis. Well, you can also do the construction if you want. You can take this ray, draw a parallel to it through the center of the lens. Parallel to it through the center of the lens. This gives us one point here, and you see that this point gives us exactly the direction which is parallel to the optical axis. So this is all consistent. Okay?
Yes.
Good.
Yes.
Now, the next one, this one. Okay? It arrives like this. We draw a parallel to it through the center of the lens. It determines this intersection point, and so this intersection point tells us in which direction the light ray is going. Okay? And we are happy because it diverges. Okay? And now the last one, it arrives here. We draw a parallel through the center of the lens. Here. It defines this point, and so this point gives us the direction of the light ray after the lens. Okay? And of course there will be a virtual image of this object somewhere here, because if we look here we have the impression that all the light rays are coming from this point, not from this point, from this one. Okay? Did you understand that? Is it okay?
Sir, I just have a question.
Yeah.
I didn't quite get why. So the light ray that just goes straight horizontally.
This one? Which one?
The one that you drew on the other side, the green one.
This one. Aha.
Yes.
Okay. This ray, okay, the direction of the ray is towards the focal point.
Yeah.
And for a divergent lens, okay, if you arrive in the direction of the focal point, then you are going to leave parallel to the lens.
Thank you.
That's why. But you can also do the construction. You can construct a parallel to that ray. You see I drew it here. This parallel, when it intersects with the focal plane, defines a point, and this point, you see, it gives you the same direction. It gives you the horizontal direction. It's the same.
Okay.
Okay? But it's just something to save your time when you have rays which are a peculiar situation, then you can do it faster. That's all. You should always check anyhow. You should always check. Okay, if you have a convergent lens, somehow your light rays after the lens if you have a convergent lens after the lens, your light rays, they should converge. At least they should converge more than the rays which came in. And if you have a divergent lens and you have light rays which come in already diverging a bit, they will diverge more after the lens. Okay? You have to have this intuition to check your drawings. For instance, here we have the rays which are divergent before the lens. After the lens, they are more divergent. Okay? They go more to the sides. They open up. So this is clearly a divergent lens. And here, if you have a convergent lens, they kind of close up after the lens. Okay? Good. This is now the same exercise as what we did before, but with a divergent lens. Okay? And we are moving the object AB from quite far to the focal point, to between the focal point and the lens. So I will let you time to do it. Okay? I'll give you 5-10 minutes. Or we can do the first one together if you want. Yeah, let's do the first one together. The first one, what should I do? Tell me. If I take the ray which is parallel to the optical axis. Oops, I wanted to do it in red, sorry. If I take this ray arriving parallel, it's going to go where?
To the focal point.
Like this. Okay?
Yes.
It's a divergent lens, so the rays are going to open up. So the direction of the rays after the lens is going to be like this, right? And the other ray which we know is the one passing through the center. Okay, and so where's going to be the image? It's going to be here, under the intersection. So this point here is the point B prime, the image of point B, and the point down here at the bottom of the image is going to be A prime. Okay, so you have, this is a very small image. Is it virtual or real?
Virtual.
Virtual. Okay, so this is virtual, and this is straight. It's not inverted. The object is up, the image is up. Okay, and so what you are going to find in the other constructions is something similar, except that the image is going to move a bit, but it's always going to be a virtual image because you have a divergent lens. Okay, when you do an exercise, it's good if you kind of know what to expect. Okay, I let you do it.
Yes.
I go do a coffee and I come back. Okay? It's terrible because sitting at home, I drink coffee all day long. I must have drank like 15 yesterday. Today I don't know, but I have to be a bit careful. But okay, I say that, but then I drink coffees all the time. Okay, I let you do it. I'll be back. Tell me when you are done. Are you there?
Not quite. I'm done.
Yes, we are there.
And you are done?
Not.
Okay. found something very nice for you guys. Okay, can we do the correction?
Yes.
And I found a very nice simulator for you. Okay, so second one, can we agree on the fact that the light ray which is parallel to the optical axis always behaves in the same way? Hmm?
Yes.
It's playing music. Hmm? Okay, so this guy is always going to go this way, and now the object is closer. Okay, and so this intersection point is going to be here, but it's again going to be a small virtual image. Virtual straight image. Let's continue. This one is not going to be much different. The ray which is parallel to the optical axis is still leaving this way, and the other ray is going this way. So we have a virtual image which increases a bit, but not much. And then for this one, now the object is at the focal point. Okay, and in that case we have an image here which is growing a bit but not much. Now what happens if you are between the focal point and if the object is between the focal point and the lens? Then it's going to start looking a bit different. Okay. No, not even. You are going to have an image which is here. Is that correct? Yeah, okay. Well, let's see that on the simulator. I found a very nice simulator for you guys. It's here. Okay? So the simulator sorry? Can you see it?
Yeah. Yes.
Well, now it's me, but sorry, it was here, it was here. Okay? I didn't know that simulator. It's nice. Maybe I will give you a lab to do about that if we don't go back to school. So you see here you have an object and you can change, oh god, you can change the position and the size of the object. Okay? So here we have a convergent lens, and this is the situation of the first exercise we did today. When we get at the focal point, we have an image at infinity, and then between the focal point and the lens, we have a virtual image on the same side as the object. That was for a convergent lens. But now what about a divergent lens? So I managed it before. I have to move the focal points. I did it a second ago. Oh my god. I changed that. Aha, okay. Now you see, if I bring the focal point to the other side, this gives me a divergent lens. Okay? And here I have an object, and in this exercise what did we do? We took this object and we brought it closer and closer to the focal point, and you see the image, it's here. Okay? It's right here. It's virtual, it's upright. Yeah, this is upright in English, not straight. Okay? And when I get with this object close to the focal point, I still have my small image here. So what we did is correct. Huh? So this is a simulator, I have to remember that. This is a simulator with which you can check all your exercises. If you do an exercise, if you want to prepare for a test or whatever, and you want to check exactly what you did, this is like having an optical system. Okay? Okay?
Yes.
Good. Let's now do exercise 11. Okay, maybe we will, it's a bit messy, exercise 11, because the scale is a bit complicated. Okay, you have to find a scale to represent things. You have a letter which is 4 centimeters high. You have a distance which is 150 centimeters. So how can we scale that down so that it holds on a piece of paper? I would suggest just to divide all the lengths by 20. Okay, so if we divide 150 by 20, it's going to be 7.5. If we divide 4 centimeters by 20, it's going to be 2 millimeters, and we can kind of represent it. Okay, but I agree that the scale is here a bit complicated. So we can say that 1 centimeter corresponds to 1/20th of a centimeter, and 1/20th of a centimeter is what? Is half, yeah? You don't see, you don't see, you don't see, I'm sorry. Voila. Okay, so in this exercise you have distances which are a bit complicated. You have 4 centimeters, then you have 150 centimeters for the distance P. The lens has a diameter. We don't care much about the diameter of the lens, but it has a focal distance of 50 centimeters. So if we want to fit all this on a page, if we divide by 10, it's going to be 15 centimeters. It's too long, so we divide by 20. Okay, so what happens if we divide all this by 20? The 150 centimeters, they become 7.5 centimeters. The 50 centimeters, they become 2.5 centimeters. And the 4 centimeters, they become 0.2 centimeters, which is equal to 2 millimeters. Okay? This is a preparation work you need to do. You need to have an idea, or you need to represent your system with a scale which is convenient. Right? Good. Now let's draw this. So where the hell is my... So we need, as usual, to draw an optical axis. Somewhere around the middle of this optical axis we put our lens. So the lens will be here. It's a convergent lens. And then we have, at a distance of 7.5 centimeters, we have a letter of height 4 centimeters. 7.5, it's here. Okay, and the height of the letter, we said 2 millimeters, so I will do it like that. Right? Okay? And I still miss the focal distance, which is 2.5 centimeters. So I can put it here and here. This is the focal point. FF. Okay? Okay, now how do you construct the image of this object? What do you think? It's going to be where, the image, in that case? Intuitively. You have an idea? Hello?
On the right side after the focal point?
Yeah. It's going to be a small image, probably because we are away from the focal point. Okay, and so it's going to be like this, and then it's going to go down to the focal point. Okay, that's one of the light rays. This is the one which is parallel to the optical axis, and then we have the other one which is passing through the center. Well, maybe this is not the greatest drawing I ever did. Okay, and you see that, oof, yeah, it's complicated. So here there will be something like this with the two lines crossing, and the object which will be, it's here, it's a very small image. Okay, it's not my best exercise, I'm sorry, actually. Okay, so image,
It's okay.
thanks, you're nice. Image is real and inverted. Okay, good. Let's now do the following one. Did I talk to you already about the laws of lenses or not yet?
No, not yet. No, not
Okay.
yet.
So before we go into these exercises, let's go back to the course and let's see what these laws of lenses look like. Yeah, I did it. I did it, but it was fast. Or maybe I did it in the video. Okay. It is usual to give certain names to the different distances we observe. So if you take your course on page 31, okay, you have this scheme. Okay? So we call f the focal distance between the center of the lens, and the focal points. We call S1 the distance between the object and the lens. We call S2 the distance between the lens and the image. In the French literature, this is called P and this is called P prime. Now, in this course that I used for the images, they call it S1 and S2. I'm more used to P and P prime, but whatever. And there is a law which connects all these quantities. The law is this: 1 over the focal distance is 1 over the distance of the object to the lens plus 1 over the distance from the lens to the image. And if you invert this relationship, you find this, or in the French literature, usually it's written like this. So you can write this if you want. Okay, actually this should have been here, but because of some printing problem it didn't appear. You have some strange signs here, so please write this law. It's important to have it in that place. Okay, this is the so-called law of lenses. It's a very famous thing. I mean, it's important, the law of lenses. Let's check this law of lenses. Okay, let's check it for the exercise we just did here, because as you see, it was difficult to measure exactly the position. So let's do it analytically with the law of lenses. Let's identify first of all the distances. So we said f is the distance between the focal point and the lens. Okay, this is small f, and it's the same on the other side. This is also small f. Okay, then the distance between the object and the lens, this distance here is known as S1 in your course, or P, and the distance between the object and the image, which is somewhere here, this distance is called S2 or P prime, depending on which notation you use. And now we have this law of lenses, which I'm going to restate here, is 1 over p plus 1 over p prime. Can you, with this law of lenses, compute the distance p prime, the distance between the object, between the image and the lens? How would you do that? Okay, you have this relationship. You need to extract p prime from that. How would you do that? Silence. Say something.
I am still drawing.
Ah, okay, you are still drawing. Okay, finish drawing. Yeah, sorry. Okay, so are you done drawing or not yet?
Yes.
Yes.
Okay, so now if you want to extract p prime from here, you can start by writing that 1 over p prime is 1 over f minus 1 over p, okay, because you put the 1 over p on the other side. And then if you want an expression of p prime, you do 1 over on both sides. So 1 over p prime is p prime, and on the other side you are not allowed to simplify anything. You have 1 over f minus 1 over p. Okay? We agree with that? Yeah, good.
Yeah.
So now let's compute. 1 over f. What is f? We can take either the reduced dimensions or the original dimensions. I don't care, it's the same. Okay, so let's take the original dimensions. 1 over f is 1 over 50. You notice that I'm using centimeters now. I don't need to transform into meters. It's not like the other chapters of physics. But if you use centimeters here, you should also use centimeters here, and the result will be in centimeters. That's the only important point. Okay, so just use the same unit all over. Minus 1 over p, and p is what? We said p is 150. Okay, and now we need to compute that. Okay, how much is that? 1 over p, 1 over 50, 1 over 50 is 0.02 minus 1 over 150. Okay, this gives me 1 over 0.013 periodic. Actually, I don't care for this value because now I'm going to compute the inverse of that, and it gives me 75 centimeters. Aha, 75 centimeters. Does that correspond to what we found? We found what? We found 3 centimeters times 20, it's 60. Okay, it's not very precise. Okay, the drawing is not precise. This is much more precise, and this allows you to compute where exactly your image is. Okay, so the law of lenses is much more accurate than all these drawings, and from now on, every time we do an exercise, we are going to check the law of lenses. Okay?
Yes.
Okay, there is another law for lenses. This is the so-called law of lenses, but there is another law which is called the magnification law. And the magnification law, you can write it in this way. Okay, I usually write it this way. G prime is the height of the image. G is the height of the object. G prime is the height of the image. G is the height of the object. P prime is the distance from the image to the lens. P is the distance from the object to the lens. And so these ratios are the same. Okay? It's all said in the text, don't worry. Okay? So now if we apply the second law here, and we want to compute, you can write it on the left if you want, okay? If we apply the second law, G prime over G is equal to P prime over P. And I want to use this to compute the height of my image because it's unclear on the drawing. Okay, so it means that G prime, which is the height of the image, is G times P prime over P, right? G is the height of the object. So let's take the original dimensions. We have it here. G is equal to 4 centimeters. And then P prime is what? Is the distance. We just computed P prime, okay? We just computed it. It was 75 centimeters. And P is the distance from the lens to the object. It's 150. What's the result? 75 over 150 is just 1/2. 1/2 times 4 is 2. So the image is 2 centimeters high. 2 centimeters high in real dimensions. So if you scale it, you divide it by 20, it's 1 millimeter high, which corresponds to this. I hope you're not getting too confused because I'm introducing many things. Is it okay?
Yes.
Yeah, okay. And
Yes.
and I did all that in the video, which is still online, by the way. If you want to watch it, you can. Okay? So drawings are nice, but the laws, they are easier. They give much more precise results, and sometimes they are easier to use. Okay, the next exercise has nothing strange. The dimensions are fine. You can take a scale 1 to 1. Okay, we have an object which is a light segment, so it's like a neon light if you want, of height 4 centimeters. We have a lens which has focal length 8 centimeters. What kind of lens is that? You remember? Focal length is positive for convergent lenses, and focal length is negative for divergent lenses. So the fact that the focal distance is positive indicates that this is a convergent lens, and you have to find the position of the object and of the image if the height of the image is 3 centimeters. You have to think a bit for that one. I give you 10 minutes. Okay?
Yes.
Allez. Oh God, it's already 4:40. God. Let's do it together because I would like to arrive to 12. Otherwise, it's going to be... Okay, let me do it, okay? Because this is not so obvious. So, you have your optical axis, and then you have a lens which is converging, okay? So, you draw it like that. Then, focal length 8 centimeters. No, it's a bit long. It's a bit long. What did I do last time? Did I scale it down? Yeah, let's scale it down by 1/2. Okay, so let's use here a scale of 1/2, which means that this now becomes 2 centimeters, this now becomes 4 centimeters, and the image height is 1.5 centimeters. So now we can nicely arrange that. We have our focal points at 4 centimeters here and here. Okay, this is F, this is F prime, right? And then we say we have a light segment of height 2 centimeters, and we know that the image, the height of the image is 3 centimeters, so half of it 1.5. How can you find where the object is?
By calculating it.
Graphically first. Graphically, how would you do that? We have an object which is a light segment. It's 2 centimeters high. Okay, so it's somewhere here. The height is 2 centimeters. If the height is 2 centimeters, it means it arrives here. We don't know where the object is, but the top of the object is at this level, above the optical axis. So we can construct now one of the rays, the one we know very well, which arrives parallel. Okay, we don't know whether the object is here or here or here or further. It doesn't matter, because this light ray is always going to be the same, and this light ray is going to go in the direction of the focal point. We agree with that?
Yes.
Okay.
Sir, how do you know it's a convergent lens?
Because the focal distance is given as positive, and for convergent lenses the focal distance is positive, for divergent lenses the focal distance is negative. Okay, that's how I know.
Thank you.
Okay, and then the other information you have is that the image has a height of 3 centimeters. Aha, the image has a height of 3 centimeters. What does that mean? Well, we took a scale, it's 1.5. It means the image has to arrive here. Okay, I don't know exactly where, but it has to arrive here. Okay, and now where is the point where we can construct an image of the height 1.5 centimeters? It's here. Okay, this immediately determines the position of the image. This is the image. It's real and inverted. Okay, you understand how I found where the image is?
Yeah.
Yes.
The top of the image, this point, which we could call A prime, this point has to be on this light ray, and it has to be at 1.5 centimeters from the optical axis. So there is no other choice, and so our image is here. And now, how can we construct where the object is? What would you do? This you should be able to find. Well, you can just use another light ray, the light ray which passes through the center, because you know that in order to have an image here, you need to have this light ray arriving like that from the center of the lens, right? And so this means that actually your object is here. Okay?
Yes.
Okay. Listen, it's time. I spent a lot of time explaining things. I'm going to stop now because I also have to go. But what I would like you to do is to do this as homework 11 and 12. Okay, and this is the homework for the 21st of April, right? Tuesday after the holidays. And I would also like you, please, plus view video which is already posted, so not today but the one which I already posted, which is a bit better structured than what I did today. Okay, because I was expecting that you had followed that video, so I was preparing to do other stuff, and well, we kind of remained stuck on that. Okay, can you do that? Can you watch this video?
Yes, of course.
Okay. Yeah, it's true. I normally don't write the homework on the classroom. Maybe I should do it, but no. You are adults. Come on. So you can write down the homework. Okay. Or I will write it especially for you, so I will put the link to that video. I will do it. Okay.
Yeah.
Yeah. You have any other questions?
What did you say? You're going to send.
Yeah, I'm going to post the homework on Classroom, so I can also give you the link specifically to that video which I prepared for last week's course and which you didn't find. Okay?
That's very kind.
Yeah, I'm so kind.
Thank you.
Okay, so have good
I
holidays.
just have a question for the report. When do we have to give it back, the report? As soon as possible?
It's not a medical emergency. Give it back during the Easter holidays so that I can correct it, and voila. Okay, because you haven't done it yet. I mean, you were supposed to give it back already a few weeks ago, right?
Yeah.
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 But okay, I shouldn't stress you, so I'm not going to stress you. But please send it, okay?
Okay, fine. Thanks.
Okay.
See ya.
Have a nice time. Bye bye. Good holidays. Bye. Bye.
Bye. Thank you.
Bye.
Thank you.